Hello, welcome to this video on related rates. What I'm going to do is go through kind of an introduction to what related rates are, go through some rather simpler examples with no story context at all, and then we'll kind of ease into some problems that will have a story problem with it, go through some rules for solving related rates problems, and then answer a couple of the more complex problems associated with related rates. So first off, related rates really hinge on the understanding of implicit differentiation, the ability to differentiate an equation with respect to a different variable. So very similar to doing like a dy dt or a dx dt or dy dx. All that kind of notation is going to be the part that really matters here. But what we're going to be doing is differentiating equations with respect to time. So everything will be a d something dt. So I'm going to start with an example where I've got v, which is going to represent our volume, r for radius, and h for height. And we're differentiating these three variables then in this equation with respect to time. So what I want to acknowledge is that we have a product rule here on the right-hand side between r and h. So we'll start off our equation. When you differentiate v with respect to time, we would just call that dv dt. I'm going to pull the pi over 3 out front, and then I'm going to do my product rule on the inside. So I'm going to take my first function, which is r squared, times the derivative of the second, which we're going to call dh dt, plus the second function, which is h, times the derivative of r squared, which is 2r, and then the derivative of r with respect to time, dr dt. That is actually it. There's not much like simplifying I can really do here, but this is kind of going to just lay the groundwork for what we're going to see and be able to apply. So in the following like story problems that we do, we'll start being given this information of what dr dt is, and we'll be given what h might be. We'll be given what the volume might be. We might have to solve for the change in height with respect to time. So it just becomes a bunch of substitution. Here's an example where I'm going to give a formula. We have y equals x squared plus 3, and our goal is to find dy dt when x is 1, given, and then we're also given something, dx dt is 2 when x equals 1. So we're given some information here. In this case, what I want to do is take the derivative of this equation, again, with respect to time. So this is different from what we're traditionally used to doing, which is taking an equation with respect to x. So deriving this equation with respect to t, I'll have dy dt equals, and then the derivative of x squared is 2x, and then we have to tack on a dx dt, plus the derivative of 3, which is 0. So in this problem, it does say to find dy dt. So dy dt is unknown to us. We do know that we want to find it when x is 1. And we are also given dx dt is equal to 2 when x equals 1. So what that's going to allow us to do then is just substitute some information in. We don't know what dy dt is. I do know I can take 2 times my x value of 1. And when x is 1, we also know dx dt is 2. And I don't have to bring down the plus 0. So I really end up with 2 times 1 times 2, which is 4. So again, kind of what I'm trying to work you into then throughout these problems is that we're taking an equation, we're going to derive that equation with respect to another variable, usually time, and then we're just going to substitute some information. What might happen is we might have to take an additional formula out, or we might have to kind of work with our variables in terms of each other. So we'll get to some of those examples as well. So in this next one, we've got a pebble that is dropped into a calm pond, causing ripples to form in circles, essentially. The radius of your outer ripple is increasing, so we know that the change in radius with respect to time, so dr dt, is increasing at a constant rate of 1 foot per second, so that is 1 feet per second. And we want to know when the radius is 4 feet, at what rate is the total area of the water changing. So when r equals 4 feet, we want the change, because it says rate, of the area as it's increasing. So we want the change in area with respect to time. So I need an equation that talks about the area of a circle in terms of its radius, and that is going to be a equals pi r squared, just the area of a circle. And we are going to again derive this with respect to t. So the derivative of area with respect to time is dA dt. I'm just going to keep pi in front as a constant here. The derivative of r squared would be 2r, and then dr dt. So I'm going to keep the pi with it, so I'm going to call it 2 pi r dr dt. So we've got our formula done. Now I can start substituting some information. So we want dA dt. So this is the unknown part. And that is equal to 2 pi times when the radius is 4 feet. And then we know that dr dt is 1 foot per second. So something that I kind of want to do back up here too is analyze our units. Our radius in this case was measured in feet, and then our dr dt was feet per second. So when we analyze our units overall, the change in area with respect to time is going to be 8 pi, and that's going to be square feet per second. So a little unit analysis would kind of help us too. We know that our area is measured in square feet. We know that our time is seconds, so it makes sense that the unit analysis would match up then, that I would end up with feet times feet, so square feet per second. So what I want to do is kind of just walk through then, okay, we're going to get into these more challenging problems. What are some steps that you can kind of do to be successful? Because, I mean, story problems are painful. Especially when you have no idea what's going on. So what you really have to do when you start these problems, and a really good way to start them, is identify what you're given. So very similar to when I identified right away here that we were given the radius is increasing at a constant rate, that needs to go off in your mind. Okay, that is a change in radius with respect to time. So that makes it dr dt, and we just label that right away. So just identifying those quantities as well as the ones that need to be determined. So far we've yet to have to make a sketch in some of the examples that are coming up. We will make some sketches that'll kind of help us determine really what we need to find. In some of those other problems, we're going to end up needing additional equations to substitute our variables into, and we'll get to some of those. But we're going to write the equation involving those rates of change. And then we're going to use implicit differentiation to differentiate both sides of your equation with respect to time. So again, d something dt is going to be the theme of all these problems. And then at the very end, just like in the last couple of examples, you just substitute the values that you're given and their rates into your equation, and you solve. And what's going to happen as you work through these problems is you might get stuck. You might have a problem that has multiple variables in your equation that you don't know. And when that happens, you might have to pull out another equation and substitute some information in, or you might have to write the equation of something in terms of something else. Meaning, you might be given a problem where it says, hey, your radius of something is 2 feet, and suppose your height equals 4 feet, you might have to just say, okay, if that's the constant rate, that means my radius is 1/2 my height. And what that does is it puts one equation or one variable in terms of another variable. So we might encounter some problems like that as well as we work through these rates problems. This next one is going to talk about a spherical balloon. So imagine a balloon where essentially air is being pumped into the balloon at 4.5 cubic feet per minute. And again, we can just really analyze these units here. We have cubic feet per minute. So I can see that my minutes are my time. This is cubic feet, which means that this would be a volume. It wouldn't be an area. This would be a volume since it's cubic. So we know then that dV dt, the change in volume of this balloon with respect to time, is equal to 4.5 cubic feet per minute. Find the rate of change of the radius. So we want dr dt. Right, want dr dt when the radius is 2 feet. So we're going to need the volume equation for a sphere. Volume of a sphere is 4/3 pi r cubed. And very similar to last problem where we were dealing with areas, this one just deals with volumes. However, we just have our dv dt, and then we're going to have a dr dt. So we don't have to pull out any other additional equations. We can just start deriving this. So dv dt is equal to, and then I'm going to do 4/3 times the 3, which really your 3's are going to cancel when we multiply those. So that's going to be 4 pi r squared times the derivative of, again, r with respect to time, so dr dt. So again, just taking the derivative, 3's dropped out. Do not forget to tack on a little dr dt. That is what we're going to have to solve for anyway, so at the very end we need to isolate this quantity. We don't have to do it right away now. We can just go right to substituting our other variables, other values in for our variables. So we knew that dv dt was 4.5. I'm going to just express this as an improper fraction. 4.5 is 9/2. And that is equal to 4 pi, and then when r is 2. So that's my r value squared. And then again, we are solving for dr dt. So it's just a matter of simplifying this, and then we're going to express our answer in terms of pi. So I'm going to leave this as 9/2 is equal to, the 2 squared here is 4, and I already have a 4 here, so that's going to be 16 pi and dr dt. And we can treat this whole thing like it's a constant. So dr dt is equal to 9/2 over, and I'm just going to bring that 16 pi to the other side. And then the 16 is really over 1, so this 2 is going to just drop to my denominator. And dr dt is going to be equal to 9/32 pi. And again, this is the change in radius with respect to time. If I go back and do a unit analysis on this, I would have, this is cubic feet per minute, and then we ended up dividing this by our square feet, because we would square this radius value. And when we take the cubic feet divided by the square feet, I'm going to end up with this just being feet per, and then the time, which is minutes. So that is our answer for this problem. Alright, now we're going to get into a problem where we have to draw a diagram, and we might need some other formulas. So this one's going to be kind of complex, but we're going to get through it, especially with the use of a diagram. Diagram is going to be huge here. So a 15-foot ladder is resting against a wall. The bottom is initially 10 feet away, and the bottom of this ladder is being pushed towards the wall. And it's giving us the rate at which the bottom of that ladder is being pushed towards the wall. We want to know how fast the top is moving. We cannot assume that the top is being pushed at the same rate as it is at the bottom. And we want to know how fast that top is moving after 12 seconds. So kind of a loaded question here. And I really want to start with just the drawing of this ladder being pushed towards the wall. I'm going to make a really weird looking ladder. I've totally got to have steps on my ladder. If I don't have steps, I don't know how we get up the ladder. Alright, so here's my ladder. And I want to just label some of the information that's going on here. So ladder is resting against the wall. The ladder itself is 15 feet. The bottom is initially 10 feet away. And the bottom, again, is being pushed towards the wall. Okay, so since this arrow is moving to the left, this is kind of weird. Since this arrow is moving towards the left, I'm going to call my dx dt negative 1/4, and then feet per second. So it's giving us, again, that rate. Since my change is being pushed towards the left in this case, I want to just write that as negative 1/4. Realistically, what will end up happening is we'll end up with a negative times a negative here, which will turn into a positive eventually. But what I want you to see then is that the ladder will be pushing upwards. So we're going to have a positive answer. As we push in the ladder is also going to go up, which would result in us having a positive answer. We do not know, or what we want to know, is the rate at which that top of that ladder is moving. So we want our dy dt when t equals 12 seconds. So the only formula that we can really use to represent a relationship of a right triangle like this is the Pythagorean theorem. So I'm going to write that out as x squared plus y squared equals, and then in this case, we have 15 squared. And 15 is our constant here. We know that as we push this ladder in, this x value will change. It's not, I mean, if we're pushing the ladder towards the wall, the 10 feet is not always going to be 10 feet. The same thing for the height. As this ladder is being pushed towards the wall, this y value is increasing. The part that is not changing at all is the overall length of the ladder. That'd be really weird if the ladder just started growing for some reason. So that's why when I write this theorem, I'm not filling in 10 squared plus y squared equals 15 squared, because again, that horizontal distance is changing. We are going to then derive this equation with respect to t. So again, the derivative of x squared with respect to t is going to be 2x dx dt. And then I'm going to have the derivative of y, so 2y dy dt. And this is where the height of the ladder is actually irrelevant, because in this case, the derivative, I don't even care that 15 squared is 225, the derivative is going to be 0. So in terms of the length of the ladder being relevant or not, for the derivative it's not. For the rest of the problem, that 15 actually will come in. So again, our goal is to find dy dt. What I'm going to do right now is isolate that quantity. So I'm going to get this by itself. I'm going to do so by bringing this 2x dx dt to the other side first. So I'm going to have 2y dy dt is equal to negative 2x dx dt, and then I'm going to divide both sides by 2y. So our equation that we're going to end up using is going to have negative 2x dx dt over 2y. My 2's will drop, so we're going to have negative x dx, negative x, I dropped a dt somewhere in there, my bad. So we're going to end up with negative x dx dt over y. So this is the equation that we're going to end up substituting some stuff into. Unfortunately, we just do not have enough stuff. We know that my dx dt is the negative 1 over 4. Great, glorious. However, we don't know what the x value is after this ladder has already moved 12 seconds later. We don't know what the y value is. We don't know how high this ladder is up the wall after 12 seconds. So we're going to need to figure those values out. So the first one that I'm going to figure out then is how much the ladder has actually moved in from the wall. So how much this 10 feet has changed after 12 seconds. Well, if we have moved 1/4 of a foot per second, so this is feet per second, after 12 seconds, I can multiply these quantities together, and that's going to tell me then how many feet we've moved, and that is 3 feet. So this ladder has slid 3 feet to the left. So the x value that we are going to use is 7. And again, we started at 10 feet. The ladder is moving in towards the wall, so I'm going to subtract 3 from that value, and we're going to end up with 7. So when t is 12, x equals 7. We also need, when t equals 12, we need to know what y equals, and we do not know the height of that ladder. So that is where we're just going to use the Pythagorean theorem again. Now that we know that this height, the horizontal distance is 7 feet, the ladder did not change the length magically. We just need to figure out this value. So I'm going to do y squared plus 7 squared equals 15 squared. Y squared plus 49 equals 225. And then I'm going to end up with y is going to be equal to the square root. And then when I bring my 49 to the other side, I'm going to get 176. And I'm actually just going to leave it like that. We could simplify it more. I'm going to just leave it as this. I mean, this is the value. We're just going to substitute in at the very end anyway. So all that we need then are our two values here and here, because that is what these x and y are. And then the dx dt is not changing as well. That is that negative 1/4. So we end up then, at the very end of all of this, dy dt, the change of the height of that ladder with respect to time, is going to be equal to negative, and then our x value, which is 7, times dx dt, which is negative 1/4, all over my y value, which is radical 176. So I'm just going to multiply all this out. I have a negative times a negative, which is positive. So I really have 7/4 over radical 176. And I'm just going to bring this 4 to my denominator. So I get 7 over radical 176. And the units are important here. This is the change up the wall, which is height measured in feet per what our unit of measurement was, which was seconds. So our final answer then, again, it's a positive value since the ladder is moving up the wall. Alright, last problem then, we've got an airplane, so diagram's already there for us. An airplane that's flying on a path that will take it directly over this little tracking station that's there at the bottom of the screen. The distance S, so this is going to be the hypotenuse of our right triangle here. The distance is decreasing at a rate of 400 miles per hour when S equals 10 miles. We want to know what the speed of the plane is. So very similar to the last problem where we're going to be dealing with the Pythagorean theorem and deriving that Pythagorean theorem. The important little fun fact here is that the plane is just moving horizontally, so our constant in this case is not going to be the hypotenuse anymore. The constant is going to be that this plane is always going to manage to be 6 miles above this tracking station, which means our y value here is the value that will remain our constant. So I want to start off just identifying again some of the information. The distance S is decreasing, that's big, at a rate of 400 miles per hour. That means that ds dt is equal to negative 400, I'm going to throw my units on here, miles per hour, and that's when S equals 10 miles. We want to know what the speed of this plane is at that time, which is going to end up being the change, dx dt, that the plane is moving at. So we want dx dt, because that'll tell us horizontally how fast this plane is going. So again, the 6 is constant. We already know that this is when S equals 10 miles. So what I can do right away is just acknowledge that, hey, we're probably going to need to know how far away that plane is at 10 miles, like how far the plane is horizontally from the tracking station. So we know that the plane is actually 10 miles away, straight line shot across S. We know the plane is 6 miles vertically above us, but we don't know that horizontal distance. So I'm going to just do x squared plus 6 squared equals S squared. Again, in place of S, I can just put my 10 there. So x squared plus 36 is equal to 100. X squared is going to be equal to 100 minus the 36, which is 64. And then when I take the square root, I'm going to get x equals 8, and that is miles. So that horizontal distance then is going to be 8 miles. So that's going to be our x value. And again, that'll be one of the values that we just substitute in later. We're still going to be working with the Pythagorean theorem. That is the only equation that we really have to model the situation. So again, think about what is changing and what is not changing. So really, I would have x squared plus y squared equals s squared. That's really what we would have here. In our case, again, the y is a constant though. So what I really have is x squared plus 6 squared equals s squared. And when I take the derivative of this part right here, because it's constant, is just going to go anyway and the derivative will be 0. So we are taking the derivative of this equation with respect to time, so 2x and then dx dt plus 0 is equal to 2s ds dt. And again, we want dx dt, so I want to isolate this piece here. So dx dt is equal to 2s ds dt over 2x. And we're just going to do some simplifying from here then. The 2's are going to drop out. So I'm really going to have s times ds dt, just like in the last example, over x. And it's really just a matter of substituting now. So we've got our values at 10 miles. So that was the thing, is we want the rate when s is 10 miles. So when s is 10, so I'm going to substitute then 10 in for my s value. We know that ds dt is the negative 400 miles per hour. And then we knew that when s was 10, we solved for our x value, which was 8. And if we simplify all this up, we're going to end up 10 times the 400 is going to give me 4,000 divided by 8. That is going to give me negative 500 miles per hour. Now, what I want to kind of go back to then is that represents dx dt. That is 100% the dx dt value. So we are correct there. That does not represent the speed of a plane. I don't know about you, but I've never seen a gauge on a car read a negative value. And that's because the velocity could be a negative value, but your speed is always going to be the absolute value of the velocity. So, although dx dt is negative 500 miles per hour, the speed is 500 miles per hour. So it's the positive value. Okay, so that is just one little thing at the very end that I need to tack onto this problem, which again, it just comes down to knowing that speed really is velocity. It just doesn't have direction. It's just the magnitude. It's just the absolute value of that quantity. Alright, and the last thing I want to note, because that's the last problem that I've got, I want to note that we are going to go through some problems eventually where we're going to be filling up like cylindrical tanks, or we might have a tank that is a rectangular prism. We could have something that is a cone. We're going to have all these shape problems where you're going to be talking about the change in volume with respect to time. And I want to just go over in an example where we do have multiple variables where we have to do a substitution. There's an example I have in front of me where we're given a diagram of a height of a cone, and then we're given that our diameter of the cone is 3 times that height value. And I'm bringing this up because the volume equation for a cone, volume is equal to 1/3 pi r squared h, which is a problem where I've got, and again, this kind of goes back to the first formula that we actually did. At the very beginning, we did derive this formula, and our answer for that was pi over 3, and then we had r squared dh dt plus 2rh dr dt. And what's going to happen when we get these problems is sometimes you'll be given only a height value and you won't be given the radius. However, the diagram is there for a reason. The diagram tells you distinctly that our diameter is 3 times the height. So if I were to have to write an expression for radius, it would be half this value. So the radius in this case would be 3h over 2. That is what you would want to substitute into this differential equation then, in for r, because then I would have pi over 3, I would have the 3h over 2 squared dh dt plus 2 3h over 2 times h dr dt. Notice what I did was take an equation which we already differentiated from the very beginning, and now that equation is just in terms of h. The only dr dt that I have is this rate over here, which again does not actually relate to the radius at all. Like, it doesn't say, hey, when the radius is 5. It doesn't have that. Dr dt would either be something that would be provided to you in the problem, or it would be the quantity that you have to solve for. But the rest of the equation is laid out that it just has a bunch of h's, a dh dt, and then our constant values. So just again, that might be one of the problems that you might encounter throughout related rates.